Остатки вашего. Да, да, да. Меня заменили.
Good afternoon, PCS members and friends. Today we have a seminar on fractional conductances as matrix versus Kubo formalism. Our scientific host today is Professor Sergey Flach, who will introduce our speakers.
Okay, so welcome everyone. It's a pleasure to have our frequent visitors back with us. Victor and Igor, let me just briefly say a few words about you guys. Probably everyone knows you, but maybe there are one or two subjects here in the room who don't. So just very briefly, Professor Victor Kagalovsky received his Master of Science in 1987 in Kharkov, Ukraine, and then after some complex path, he but started his PhD and finished his PhD in 1995 in the Ben Gurion University in Beersheba in Israel, and then he moved on. He worked for some time as a postdoc in the group of Hans Weidenmüller at the Max Planck Institute for Kernphysik in Heidelberg, and then he had various other positions, and then he became a senior lecturer of physics at the Sami Shamon College of Engineering, and where he's ever since, and moved through the ranks, becoming associate and full professor, and is since 2014 also the head of the Department of Electrical Engineering and Electronics. Now, this is an unusual seminar. We have two speakers. Let me just remind you about that, but actually, two authors, one speaker.
Yes.
And I was told that the second non-speaker, but author maybe will answer the questions or ask questions, we'll see. So the second author is Igor Yurkevich, Professor Igor Yurkevich from Aston University. And where is my secret files here? Right, so he finished his PhD in 1988. Again, of course, it starts again from Kharkov, Ukraine, and then he moved to other places, including also Bar-Ilan University in Tel Aviv and the International Center for Theoretical Physics in Trieste in Italy. And then from 1997 on, he moved to the islands, to the UK, to the University of Birmingham, and since some more recent times, which I can't tell exactly when it happened, I'll probably just have to take the end of. So since 2013, I guess, he is with Aston University, where he is an associate professor of applied mathematics and data science. So doesn't sound very physics-like, but he's still a physicist. So with that said, we will listen today to some ongoing story on fractional conductances as matrix versus Kubo formalism. Let us welcome our speakers.
Okay.
Please.
Let me first start on behalf of both of us and just thank Sergey for this coming opportunities, and it's really a pleasure to be here, and the atmosphere of research, really, it works. And this is exactly as you said, this is ongoing story. And we were talking about this, and Igor, actually, if I remember correctly, was the first one who was talking about this on the joint, very special first joint seminar between your institute and Dresden Max Planck Institute. The very first seminar was Igor's presentation via Zoom, for sure. And so, but we are really, so this research started actually in Dresden in 2022, and it continued here. And we really believe that we went a big road, and we are now finally close into the finishing line. And I hope that I will be able to explain at least some points for you, which are very important. Okay, so as usual, we start what was the motivation, the experiment, which produced this incredible, strange ratios with fractions, which usually observed in fractional quantum Hall effect, but now there was no magnetic field. We're talking about the existence theory and what was not a problematic, but at least what was strange, and we were trying to clarify it and to explain that the result should be only this expression and nothing more. So this is what is called generalizations, and which will lead us to conductance. I will also present, because this will be about the perturbations which must be relevant, otherwise you will never observe these fractions. So there are a lot of conditions for those numbers, and especially, I mean, one of the most incredible results in this experiment was that you have even denominators, and if you know, and obviously all of you know, fractional quantum Hall effect is always an odd denominator. So, as usual, this was the experiment. I'm sorry for the quality, I don't know the quality of this graph. And obviously, who else, if not Mike Pepper, who would measure fractional conductance? It was not for the first time in his life. And so this was something very strange. They observed in the quasi one-dimensional system, which was produced very easily. You all know gallium arsenate. You know that if you make sandwiches, you produce a two-dimensional electron gas. And if you put electrodes, special different electrodes above, you can construct a very narrow channel. You can make it wider, and they were playing with this. They were also, in their constructions, they were also changing. This is actually a split gate, so they were changing the symmetry of this channel, and nevertheless, they were able to observe plateaus. And plateaus are usually the sign of the quantum Hall effect. And so something remains constant, doesn't matter what you do into a system. And the most incredible was that they observed at least two, they observed much more, but 1/2 and 1/6. This was something very interesting and very important. So first of all, so what is the theory? What can you apply to explain it? And obviously it's one dimension. And obviously it was strongly interacting system. So the proper tool to it is Lagrangian liquid approach. And so first you need to recollect what are the results, what are the main directions. Lagrangian liquid interactions are characterized by the Lagrangian constant if we're talking about one channel, and it tells you what is the interaction of the system. And there were times when people believed that this value K is also the value of conductance of your one-dimensional system. Then it took some time, and exactly 30 years ago, 3 different groups, and now we are extremely, not just politically correct, we are correct. These 3 different groups have produced the following result. Usually we still call it Maslov-Stone approach. They have shown that if you start with the most general Lagrangian liquid with only forward scattering, and you attach very far away adiabatic constants, and indeed this experiment is for very long, clean systems. And then if you calculate Green's function, and and then you apply Kubo formula. So here the first time it's coming the title of the talk. So this was a Kubo formula approach. They were able to show that the conductance doesn't depend on the interactions, because when you attach your electrons, this is already two-dimensional liquid, and its effective Lagrangian value is 1. And this was the main result, and this was very important, but this was known for many years. Then,
Sorry.
yes, please. Yeah.
It is the previous slide, the stupid question.
I came back, yeah.
Yes, please.
The previous, you mean the experiment? Sure.
Yes,
Yeah.
here you think that this even denominator is the quantized value, or is the parized with this Franchi gate continuously, but it has the even denominator by
Okay.
chance.
Their main message was that this is a quantized value, but the accuracy, and I will be talking in detail later, the accuracy is not the accuracy of the quantum Hall effect. It's not 10 to the minus 7. And this is very important for the explanation. This is why I will suggest to you a number of explanations. But which year it was? It's the first one, I guess, this was 2019. They continue measuring it and they improve the accuracy. So actually, they make those platters flatter and flatter, and they still claim that now the accuracy is better than 1%, maybe 0.5% or something like this. Okay, so this is just for one channel. Obviously, no chance to have something here.
Can you
yeah, sure.
remind us again? So the setup of the original experiment. Why are we getting now down to 1D? So what makes it 1D like in the original experiment?
I don't have.
Yeah, again,
I'm sorry.
You can just
No, I mean, no, I don't have to. You have two-dimensional electron gas.
Yes.
And you put above gates.
Yes.
And you create a very narrow
Make
channel.
a narrow, more and more narrow channel.
More and more narrow
How
channel.
narrow?
Ooh,
Are we
no,
talking?
I will not tell. I'm sorry.
Microns.
Still microns. So that's the width of the channel
The width?
as compared to
Which is the length?
Half of a micron width and length, they approximately the same.
Yeah, but I mean, the size of what's the size of the plaquettes, you say, the 2D thing?
Few microns.
Few microns, and we talk about half micron, something tiny, more tiny. Okay, thank you.
No, this is, I'm sorry, I forgot, that's the first message was that Igor will answer the question.
That's why I'm here. Yes.
Yeah, exactly, this is the very reason.
And yes, Igor, and let's continue. And this, in this paper, in these experimental data, can you please show them again, the experimental data?
Yeah, sure.
So what is the voltage on the x-axis?
And this is
In fact,
split gate.
good idea.
Yeah.
Can I draw
Yeah,
the
yeah,
finger?
exactly.
So, here. That's the sample, right? And then
Okay.
there are two gates.
Okay.
And there is a gate from below. So,
Below.
or from the top. it doesn't
Okay,
matter.
yes, from
There is one voltage bias which is called top gate. You change just homogeneously density in this two-dimensional system. On the top of that, you apply bias to these two Euclid barriers.
Right.
You change they
width.
become higher and they move in the direction to each other.
Right.
So this is channel through which you have current,
Yeah.
and you can change widths and you can change height by top gate. This is split gate. This is gate
Okay,
which
this one.
changes the width of.
So you make it more and more narrow or less narrow as you move.
Exactly, they can
Yes.
play with it
They have-
and sorry.
They have even more freedom. They
There is also
place
asymmetry gate, yeah?
asymmetry. They can apply asymmetric split gate,
Yeah.
and it also they
Okay.
check everything.
And to continue to answer your question, they were actually able to play and to show how instead of one channel, they obtained two channels. They were able to show that they now have zigzag state or something like this. How? They would apply here magnetic field. And so these guys will go, and if there are more than one channel, you get more than 1 point from the deviation by magnetic field. Okay, so one channel we don't have, we have just one of this, and obviously we'll need something else, but then there is this generalization, and I will come to it twice, because actually these, if we now have, if we now have an interaction between different channels, I will come in more detail to this, because here is an explanation on the language of S matrix, another title of the talk. But actually, I will show you that it is even more important to explain it when we apply Kubo formalism. So still, if there is only forward scattering, we can generalize this Maslov-Stone approach and show that still we have that in the infinity it goes to the unity. There is no interaction in the infinity, and then one can show that still the current is moved by all n channels. So instead of one for one channel, you can have n for n channels. Obviously, I'm talking the units of E square over h. Okay. Then this is already something which was produced by two guys, Shavit and Oreg, who said that let's look for a two-channel backscattering. Now there is additional word, backscattering. So now it's not just forward scattering. And then they suggested that they can describe it everything in the, I called it intra-channel backscattering. You see that there are n1 particles backscattering in the first channel and n2 particles backscattering in the second channel. It is described by this cosine. And this is a very important point because obviously we are still in physics. We need conservation laws, and so we need conservation of momentum. So if we hope that the velocity in the first channel and the second channel, they are different, and if we check, there are two chances, or we can play with backscattering in two different channels, different numbers, or second opportunity, if this system is rather clean, it is called umklapp process. So you can be changed on the discrete lattice. You can change not to be equal momentum change, but equal to the 2 pi times the wave vector of the lattice. And so they have shown that if this perturbation is important, relevant, and I will talk also about the idea what is relevance means in one-dimensional systems, then in this case, they were able to show that this is the answer. And you can check just with the most simple numbers, 3 minus 1, 3, 1, you will get 2 over 5. This was the very first result to explain one of the answers. And in the next transparency, I'll show you more details how they did it. So this is the figure from their paper. So this is their definition of the relevant perturbation. And they said, what is relevant? What does it mean? If the perturbation is relevant, the amplitude, the parameter which stands before cosine, grows exponentially when you decrease temperature. In this case, the only opportunity to save your Hamiltonian is to make your cosine equal to 0 to minus 1 to fix it. Fix meaning freezing the corresponding field. So they said, if we have frozen, if we have this field being frozen, then we can look for the field which is orthogonal to this one. Because orthogonal, it will not speak with the frozen field, it will remain free. And in this case, they were able to show that you can calculate the conductance of your system either by the number of channels which you have before, minus what you lost to the frozen field, or directly by the calculating of the conductance of the remaining free channel. This is a very important result, and it turns out that it explains actually, as I said, because the experiments are being continued for 6 years, they already found, for example, another answer, which is 1 over 5. And if you look here, actually you can get it 2 minus 1, 2 squared, 1 squared. But this is very special, it's forbidden, because they need to be of the same parity. So it's actually 4 minus 2, but it will be the same result. So now, at least what the experimentalist who works with Mike Pepper, who is in charge of this experiment, Kumar, he is saying that now at least they have explanations of 2 numbers, 1 over 5 and 2 over 5.
So you say that the N1 and N2 must have the same parity, yeah?
Yeah. This is not trivial. This is not trivial. We can.
If you
prove
play
it.
through all of them, all combinations of both odd and both even, I mean, what kind of set of numbers do you get?
let me continue and I'll show you, and you will enjoy it, believe me. Actually, today I have shown it once here, so we erased the details, but at least I'll show you something. Okay, so this is very nice sketch of the conductance dependence on the temperature. So here, this conductance of the fractional conductance, and they were also able to show how the system behaves at lower temperatures using the reformalization procedure. Very nice results. Obviously, for high temperatures, you don't have any relevant perturbations, so you are back to 2. Funny enough, also for 0 temperature, you go back to 2. But this is just different result. And here, the first small answer to your question. This combination never produces you even denominator. This is this is mathematical induction, something which we learned, I don't know, in the grade number 7 or 8 in school. And this was a nice, but I will not present it, I erased it today. But I'll show you few more details. So,
sorry.
Yeah.
Short question. The physical meaning of N1 and N2, for example, the spin up channel number and the spin down.
Exactly, you're absolutely right. We can think about, we can speak in different languages, but you can define channel like spin up and spin down. You can define channel 1 with spin up and channel 2, you can define channel as you wish. Here, for example, I will show you in a two transparencies. There is actually some strange definition how we define channels, but yeah.
I don't think that you can define it. It's not exactly one-dimensional, it's quasi-one-dimensional, right? So you have to take into account transverse quantization.
Yes.
So it might be just another label for counting channels. Transverse quantization.
Yes.
And if there is no magnetic field spin, in strong magnetic field, just transverse quantization.
Why if there is a magnetic field?
If strong magnetic field, you have polarized system, all spins up.
We still have transverse quantization.
But it doesn't introduce a new label, right? All spins up.
Yes, but you can.
But transverse quantization.
So if all spins are up, then what?
Then just forget about spin.
What will happen? No, but what will happen? But you can still get plateaus, right?
Yes,
Yeah. That's what I mean.
Yeah, absolutely.
Sorry, I'm also a little bit lost. So now if N1 is equal to N2, then no conductance. So what happens?
So it's very easy to understand if you look on the definition. So sorry, first I answer what is N1 and N2. N1 is the number of particles which were scattered in the first channel, and 2 is the number of particles which have been scattered in the second channel. Okay, this is point number 1. Now to your question. If you have N1 equal to N2, it actually means that there is a backscattering of the center of mass. So you freeze all both channels when N1 is equal to N2. So this is the difference. And this is an important point. So I will come to it. But we can also speak on the language that we have N1 particles which were moving in the right direction and N2 particles moving to the left direction. This is one possibility. Another possibility, N1 particles in the right direction, N1 particles in the left direction in one channel, N2, N2. They lead to the same result for the conductance, but those are different processes, and I will show you, because they are different processes, their relevance is different, so you can choose what is more probable. Okay, so here is generalization. So obviously, we understand that if we want to explain more than just 1/5 or 2/5, or as Sergey asked, so you can have a lot of, but always odd denominators. If we want to hope for something more, we need to introduce channels. So now, and not just channels, now we understand what is the procedure. If you have something inside your cosine, you say, this is my new field, and it is being frozen. But we already know that if only one field is frozen, the answer is n1 minus n2 squared. So no even denominators. So what is the hope? Maybe we have a lot of cosines, different ones. Then we need to be very accurate. They need to coexist. They need to talk, to speak to each other. Then, so I will show you all the conditions, but how we approach this, the idea is the same. So now we'll move to new fields, and on the language of the new fields, those ones will be frozen. Hopefully, the remaining ones will be free, and we will be able to proceed. How we approach? Very easy. If this is the electrode from which the particles are going to the right direction, we called this I to the right, and we called it that it has the voltage V1. Here is the second electrode, where we're moving in the left direction. We called it V2. And these are just, they are called charge vectors. Just all of them are ones. And obviously the idea is if we will be able to calculate the scattering matrix between those parts, then we will be able to calculate conductance. This is a very important point. So what we will need also, this is just definitions, and we can also work, so this is n-dimensional space, the number of channels. You have n right movers and n left movers. You can also speak on the language of 2n. You define this new effective charge vector, and now you can combine exactly what I was telling to your question. This you can combine right movers and minus left movers. So this is just the definition, nothing more than that. Before I proceed, I want to underline something. What was done in the work by Shavit and Arek, and before that there was another work also. He was part of it. The two other guys were Adi Stern and Sella. They have suggested how to treat these systems where something is being frozen, but the direction was a little bit not strange, but not convincing. They were saying, okay, something is sitting inside cosine. This is a frozen field. Let us now define a free field. And their definition was, we wish to define it this way. In the paper of Oreg and Shavit, it's exactly orthogonal, but in the paper of Stern, it wasn't not even orthogonal. And so the question was, if I define a new field, which I have some kind of arbitrary definition, I have to say I have to get the same answer. I cannot depend on my choice. So obviously, this is why important this Shavit-Areg approach was. That much better way is to take the number of channels and to subtract frozen channels, because frozen channels is what you are given. And this is exactly which I will show, which Igor developed, and this is one-dimensional and, in my opinion, very nice and very convincing. But this is an important point. So how can we write it down? First of all, there are conditions. You are talking about perturbation. Perturbation is to kill some state and to create another one. The number of creation and annihilation operators has to be the same. Otherwise, you don't create particles. So this is the condition for the neutrality, we call it. And this is on the new language, if we work with this n-dimensional vector. If the perturbation has to be frozen, it needs to commute with itself. So this is additional condition. But lucky for us, it turns out that it's actually even better. This is a private case of the Haldane criterion. What was Haldane criterion? The idea was the following. If you have different cosines, in order to coexist, these definitions have to commute with each other. And obviously, for one perturbation, it needs to commute with itself. So this is it commutes with itself. This is the definition how different perturbations commute with each other. And this is simply on the new language. This is very easy then to make calculations with this stuff. So these important points that we need to always to underline. You cannot just say that I have two such perturbations. You need to check that they satisfy all this stuff. Okay, so now what we do, the idea is the following. Obviously, if we start with original fields, and these phi are original fields, and some of the combinations of these original phi's has to be frozen, it is natural to define the new fields, part of which will be those frozen fields. The rest of these new fields will be, as we hope, free fields. But what is important for us that we don't care. We will show you that it doesn't depend. So when we create this matrix M, some of its columns are exactly the frozen fields, those guys. These are Ka are just the columns of this matrix. The rest, it's up to you. Obviously, it needs to be orthogonal or something like this, but we don't care. We will show you that the answer depends only on this. And this is what is important. Then you make the same step. We are not saying that we did it. It says, you say the following. So now we are working with new fields. In new fields, part of them are frozen. They do not contribute to the conductance. They are completely backscattered. Part of them are completely free. So they contribute, each one of them contributes completely to the conductance. So you, with a trivial, this very nice but simple idea, you say that the corresponding scattering matrix in the new fields will be either 1, 1 on diagonal for the free fields, or 0, 1, 1, 0 for the completely backscattered fields. And so we can write it down immediately. The question is, in order to calculate conductance, we need to go back to the original fields, because in the original fields, we know how much current each current bears and brings. And so the idea is this one. This is a nice picture of Igor. We can write it down in a trivial way, but there is no direct way from the new fields scattering matrix to the original field scattering matrix. But from the scattering matrix for the new fields, we can define transfer matrix for the new fields. And from here to here, it's already a very easy one. And obviously from here to here, I don't need you to explain, because this is our main formula. And here you can say, wow, you have actually this matrix, I don't know, rotation matrix or whatever, call it, from which transfers from the original fields to the new fields or back. And in this case, I have some choice inside. Lucky for us, what will come to the main result of the scattering matrix, and scattering matrix I also don't care, I care about conductance, will depend only on the transfer matrix block, which we call 2, 2. So the last one, and you will see, I'm not sure, it's just algebra, but you will see that it brings you to this answer. And this answer is projector. And what is this projector? I remind you that we have relevant perturbations. We call them vectors Ka and Kb. So the product of Ka, Kb is simply the matrix of this subspace. The direct product of Ka, Kb times the inverse matrix of this, it is the projection operator on this subspace. So from all our possible vectors, we need to project on the subspace, which is, how should I say, unilaterally, or what better word? One-dimensionally defined. So there is, I don't have any choice here, freedom of choice. So in this case, we have exact definition of the scattering matrix. And if you look at this chirality vector which we introduced, the first n ones correspond to the right moving, and the next n ones, minus one, correspond to the fields flowing to the left. It will be important, and then I have to apologize because next to transparency, I did for myself in order to explain not to the level of this audience. So how do we calculate conductance? Yes, please.
Sorry,
Yeah.
did you simply do the unitary transformation to get the new field?
It's not unitary exactly. It's pseudo.
It's not.
Pseudo orthogonal. Yes.
Pseudo-orthogonal.
Yeah.
So you have some bare channel basis and
Exactly.
you do some.
And we check that in the new basis we have the same Lagrangian PQ terms, and we call them. So yeah, exactly. So it's almost orthogonal matrix. Sometimes it becomes orthogonal, but we call it pseudo orthogonal. Okay.
So in the beginning, we assume that the cosine and formulates are the
Once again, sorry.
we assume from the beginning that all the cosine term formulates are the or not.
I don't hear.
Cosine terms, does it commute with each other or not?
Exactly. Once again, cosine terms describe perturbations, and I have shown you that there are conditions for this perturbation to coexist with another perturbation. So we are talking only about perturbations which can coexist. This doesn't answer your question.
Cosine term that will formulates are the
That's exactly the point. You're absolutely right. He wants to freeze field which is sitting on the cosine side. You want to freeze one field, you want to freeze another field. You cannot do this if they are.
that I agree.
That's point.
But the point is that because you assume this from the beginning. But what happened? Physics system not very with your assumption. Then what happened?
If they do not commute, they will not coexist. So one of them will be relevant, the second one not doesn't.
Okay, my point again, system, but that's how I understand. If you cannot freeze two fields, then you have to look at the amplitude of each perturbation and freeze the strongest one.
Right.
Okay, so how do we calculate it? This is a nice trivial picture. So we have current IL flowing from the, sorry, it's not from left, but because it runs to the left, so it goes from this electrode, and I right comes from this electrode. So how do we calculate the current? Obviously, the current, you can calculate, there is a continuity of the current, so you can calculate it, all current goes to the right, minus all current goes to the left here. You can calculate it, all current goes to the right, minus all current goes to the left here. This is exactly what I'm showing you here. And and obviously all these IR guys are bringing with them VR because they are E squared over H. What? Stop. Oh, you just take it. Exactly. So each one of them brings E squared over H times the voltage which it feels. And those guys, exactly VM. Now have a look. So who goes to the right? Let's say that going to the right is +1. So I am taking this huge, remember this vector which +1s and -1s, and I have to kill all -1s. So I multiply it by xi, and these are the guys, I have n ones and n zeros. So all the guys going to the right. This guy goes to the left, so it comes with minus, and obviously I have to kill all pluses from first one, and so I add this one. So this is the definition of the current, and it turns out that you can write it down like this. Maybe you recognize that this is the difference of potentials, which will hopefully come to the conductance. So what I do next? It stopped working completely. So, okay, no problem. I will maximize. I'm capable to come. I didn't push anything.
Oh, for sure you did something.
Okay, let's go. No, it works.
It works?
Okay. So, what I will need more, this stuff, because I am going here to talk about what being backscattered, I will need this scattering matrix, our result. Okay.
Sorry about the
Yeah.
stupid question. So the right part of this formula, VR plus V left, VL should
No,
be
this
zero?
is, no, this is just, no, this is not the current. This is the vector of currents.
Okay.
Vector of currents show you the guys moving to the right and to the left. The vector of currents. This is 2n dimensional vector.
Okay.
You have n IRs and n ILs. With
Fine.
moving.
So the current is the difference between them.
When I will calculate it, I
Ah.
didn't calculate it.
Okay.
It's still vector. Give me a second, we'll speak. It's not even the
Because
first-
like the second term
This is not a
violate.
bachelor degree talk. This is about, I don't know how many years we have in school, but maybe.
Because the
Then-
second term violates the Gaussian invariances.
Yes, but this is correct. If you check, you can write down. If you want to write two n numbers, you will get exactly this.
Okay,
It's
okay.
okay. Okay, so the current continuing here. I calculated first. Now these are numbers, so here's the difference. So I calculate here the difference, or I calculate here, but because it's the same difference, I can write it down like average of two differences. And if I write it like this, so what is JR? This is JR is the total current flowing to the right. So this is exactly what was written before. And it has to be multiplied by T plus sigma T. This is, let me show you. This guy, T plus T is a vector which is 1, 1, minus 1, minus 1. Here there are n guys and n guys. I want only first n guys. So in order to erase this, I add here sigma T.
You should not.
I don't push anything. Okay, so you write it down slowly and nicely. You continue, and you finally obtain this result. That you take this strange T vector, you multiply it by the unity matrix, and you obviously know what this unity matrix brings you. It just gives you the number of channels, the number of states, 2n states, and here is minus our beloved projector. So now all I need to substitute here I from the previous transparency. This one, which you didn't like, but I like very much. And if you substitute this expression here, you will have T, P, T. You will have T times sigma T. And there are some nice results. For example, this is exactly 0. And this is exactly 0 by different reason because of our neutrality condition. Remember, I was talking about the number of annihilation and creation operators is 0. And if you substitute it here, this is what you get. And now this is current, this is voltage, so everything the rest is conductance. And this is the result of the conductance. And as I promised, it doesn't depend only on the what you are asking, only on the perturbations which are given to me, which work, nothing else. So I don't need, I can invent any free channels I wish, the result will be correct. This is very important point. More than that, as I told you about these two previous blocks, there it was important that you have new field orthogonal to the frozen one. Here we don't care. And also one more answer to your question. Our perturbations, we don't even need these k vectors to be orthogonal. What is important for us? That they are not proportional to each other. But if they define for us a subspace, The answer is that you have n channels in the beginning, and here you subtract what is frozen. And this is,
Sorry.
Yes,
Is the information about the is the mixed backscattering to the mixed channel, the different velocity. This information
you're
is
absolutely right. But here, as you have seen, because we are using scattering matrix, we don't have velocities. We have the because when you are talking about the current flowing from the electrode,
yes.
the current and one channel is E squared over H times the voltage of this channel. If you're thinking about the velocity, obviously you can say that this current is velocity times the density. But density in one dimension is inversely proportional to the velocity. So it's being cancelled. This is extremely important question. It was already been asked here. And this is, but in this approach, there is nothing. I mean, I don't even need to pronounce my last words about this V times density, that it cancels each other, because I just write down the definition. Current is voltage times conductance of the original channel, which is 1. So that's it. But your question will come later when I will tell you about Kubo, and this is so I hope that this answer will help us later. Okay. So, if we want to think about the same language, but we want to use a Kubo formula, exactly as was done 30 years ago by Maslov-Stone, obviously in their case there was no backscattering. So the answer was simply Lagrangian behavior at the infinity, which is 1. So the answer is 1. We now say the following. If we need to address multi-channel Lagrangian liquid, we write it down here. It is written in the language of the fields phi and theta. You can rewrite it on the language of right and left moving fields. It's all the same. What is important here, that in this case, this still has no backscattering. This was our first step to approach it many years ago. And this is how you can describe it. How you can describe it. It turns out that this is not a collaboration. This is a paper of Igor, let's say, 10 or 15 years ago, where he suggested that you can describe it not with 1, because you have multi-channel. You don't have one Lagrangian parameter, but you have Lagrangian matrix. And this matrix is defined in the following solution of this equation. And it turns, this is very easy. This is the matrix which describes you electron-electron particle-particle interactions. This is matrix which describes you current-current interactions, as Gimarki explains in his book. It turns out that the solution is trivial. This took us some time, and still it's very nice that there is a solution here. And then with the help of this matrix, you can describe any perturbation you have in your system. And then you can say the following. If my system has only forward scattering, I can think, because it's multi-channel, but still I can use arguments by Maslov-Stone, and I want to can calculate the Green's function. And this already we did, at least some part of this I participated, and we did it together, and Maslov-Stone generalized. You can show that when you develop the Green's function as a series, the coefficient proportional to 1 over omega, which you multiply by omega in Kubo formula, it turns out that this is exactly like was done by Maslov and Stone for one channel. They got 2 pi I times k Lagrangian number. We have shown that it is Lagrangian matrix in this case, but obviously we can say that if we go far away, Lagrangian matrix will become trivial unity matrix. So at least for n channels, we can hope that we will get this result. So now, can we do the same Kubo formula for the case when we have backscattering. The idea is the following. This is the definition. This is the definition of total current. You see here, you have vectors with as a time derivative of the bosonic field. When you have some fields being frozen, you are left, you have to go to new fields. You see this tilde, and this mu now is talking only about remaining free fields. Now the point is the following, and here is exactly what will to the question. If we still believe that for the free fields, the arguments I have shown you on the previous transparency, that we can show for the free fields, only for the remaining free fields, that we can solve the Green's function and show that it's proportional to the Lagrangian matrix, and at the infinity it becomes unity. In this case, we can say that this parameter, which comes to this is the definition of the conductance in Kubo formula, and then we can say, we can show that this guy, the correlation function of these free remaining fields is proportional exactly to what had been shown few transparencies ago to the matrix of this free field, not a frozen field, obviously a free field. But what is important, it does not be multiplied by anything. It is multiplied by unity, because we believe that in infinity we are in the Maslov-Stone regime. In this case, you can calculate what is the total conductance, and you get exactly the same expression as before. What is the difference? Few transparencies ago, I was suggesting to you to project on the frozen subspace. Here is projection on the free subspace, but lucky for us, we know that if we combine projector on the frozen and on the free space together, they will give us a unity matrix. So if we substitute here, instead of projection on the free space, a unity matrix minus projector, which you already used before, you get exactly the same answer as from scattering matrix approach. Here, I'm not talking about the velocities of the channels, and here, but in my opinion, because the first proof is exact, the way that we receive this result in this way proves that this is correct assumption, that this Kubo correlator is exactly the matrix of the free fields. Okay. Now back to N1 minus N2. So if we know this is the, sorry, it should be G small. So the conductance of the system with N channels, which has only one relevant perturbation, but many channels, you have a combination of those numbers N1, and it runs to N capital. So in order to answer about the number of different fractions, ratios, what about the denominator? So now you can show it in a second. You write it down as you substitute here even numbers, or you substitute here odd numbers. Doesn't work. No, doesn't work. No, doesn't work. So this is the very first result that we've got, and it really works. And why it was a good sign? First of all, this was, as I told you, it was a mathematical induction, trivial proof for, I don't know, 10th grade or maybe 8th grade. But the result that the numbers are actually the basic numbers, because what is the smallest number of your particles being backscattered? 1, yes? So if I have in 4 different channels only 1 particle being backscattered, and then I need to add just 2 particles in the last channel, and I get exactly 1/2, I think it's a good sign. It's not a proof, obviously. So, but because n equal to 5 is not good, because we believe to the experimentators, and they are saying that there are a lot of spins there, so all states are spin full. So we have spin up and spin down, which means that we actually have 3 channels, which 2 spins in each one. So the number of our channels is 6. So this is the answer. So how can we construct this? So we have this 1/2 and we have 1/6. So 1/2, if I'll take only the previous one, it was given me 1/2 for 5 channels, but I don't have 5 channels. I have 6 channels. So I need to cancel 1 channel. So I need to cancel 1 channel. Then it gives me 6 minus 1. And then I substitute this first perturbation, which gives 1/2. If I need to have 1/6, it was an easy task. Everyone knows that 1/6 is 1/2 minus 1/3. So we needed to find something which gives us 1/3 and to subtract it. And it turned out that this is exactly it. So we have 1 channel being closed. This is -1. Then we have this guy, which is -1/2. So we needed to find a perturbation. This is answer once again to your question. This guy is orthogonal, so it definitely commutes with both other perturbations. And if you substitute it here, you get exactly 1/3. So 1/2 minus 1/3 is 1/6. Once again, obviously, if you are thinking in order to explain the experiment, you need something improbable. So I don't know how to convince you. This is rather reasonable. That 1 channel has been closed, it's okay. The coexistence of those 2 guys, I'll show you how to calculate the scaling dimension. You know, the scaling dimension is the exponent which tells you if your perturbation is relevant or not. So
In the experiment, did they try to measure the thermal conductivity?
no, not at all. Okay, so yeah.
One question in the previous slide, to plot the theory calculation or experiment?
No, this experiment.
Experiment.
No, this is copy from the experimental paper.
I see.
No, I just for this one, yeah, sure. Okay, so how so this was the very first papers, they produced something like 30 or 40 different ratios. They observed 13/41 and numbers, but then they wanted to clarify. So those are the main numbers: 1, 1/6, 1/2, 2/5. Now in the new paper there is also 1/5, and there are a few more results. So how can we explain this? This is easy. 1/2 is easy. This is also easy. And here is 2/5. And it's also easy. You just take the result by Shavit or Reg, and you simply close 4 other channels, and then you get this 2/5. So now, which one of this work? Okay.
So do you have a like different way to confirm your Chap vector, or is it that you have a formula to satisfy the experiment result, but you have another way to confirm your Chap vector?
Obviously not. I cannot prove that this is a no. What I can do more, I can show you what are the chances that my perturbation is relevant. At least this is additional information which I can provide. But obviously, I cannot say that this is the perturbation. Unfortunately, we don't even know the number of channels. Right. They claim that they have only 2 channels. For 2 channels, we have a proof. There is no 1/2. there is no 1/6. So I will show you that maybe they are not exact, then probably two channels. On the other hand, we have their experimental data, which I have shown you here, which shows exactly 5 different points. 5 different points means 5 channels in my language. So more than that, and the 6th one is closed. So maybe this is, but we cannot connect. Nevertheless, that we enjoy talking to Mike Pepper every summer, and Igor is in touch in the UK. But we cannot clarify, not from him, neither from Kumar, what this picture does it corresponds to which previous experiment. So I don't know. Okay, so how one relevant perturbation. This is a paper I was talking about. So on the language of, so this is the right moving particles. And one right moving particles, for you, right? Right moving particles and one particles in the first channel, and 2 left right moving particles in the second channel. You have to add what is going on to the left moving particles. So there are 2 possibilities here only. Either left and right are exactly the same, or you interchange the numbers. Obviously, the answer for the conductance will be the same. But this combination in this paper describes, as I told you, intra-channel. So N1 particles in the first channel and 2 particles in the second channel, backscattering. This one in this paper describes intra-channel. So particles from first channel being backscattered to the second one and vice versa. And when you think about it, it corresponds to different bosonic fields. Intra-channel is always phi right minus phi left, or phi field, or it is called charge field. Intra-channels includes also the field theta, or if you wish, phi right plus phi left. And those fields correspond to different scaling dimensions. So it means that those perturbations will have different probability to appear. And I just show you just one example, that according to this definition, this is the scaling dimension, which you compare with the dimension of your system, because it's a clean system, it's one-dimensional, the one dimension is the time dimension, so you compare it with 2. If delta is less than 2, your perturbation is relevant. The answer for these guys is here, and it includes only Lagrangian constant. The answer for these guys is here, and it includes Lagrangian constant, and it's inverse. Once again, I don't know, for the exercise for the 5th grade, you understand that these are different numbers, and it turns out that, for example, for k larger than 1, this scaling dimension is always larger, which means that this process is less relevant. So actually, this process can occur, in our opinion, before that. And obviously, if we are talking about 5, 6 channels, you obviously have the scaling dimension becoming larger and larger, and it means it's almost for sure irrelevant. Okay, so the value of experimental uncertainty. If it would be the results of the Nobel Prize, and actually, in my opinion, at least one of the authors here in this experiment deserved at least twice Nobel Prize. If it would be the results of the Nobel Prize for quantum Hall effect or fractional quantum Hall effect, where the accuracy is the largest accuracy on Earth, you know that now the unit of the resistance, 1 ohm, is defined as 1 von Klitzen, and this is the accuracy 10, I don't remember, but it's minus already larger than 10 something. So in this case, obviously, this is one-dimensional answer. This is an absolute answer. You need 6 channels. You cannot explain 1/2 and 1/6. So if the accuracy of the experiment would be perfect, then we would say that, guys, you don't have 1 channel, 2 channels. you have more than two channels for sure. Otherwise, you cannot get this even denominators. If the accuracy is not ideal, I'll show you just an example. It has nothing to do even with this paper. This is the famous approach of which perturbations Theo and Kane suggested in order to describe fractional quantum Hall effects. So you can see here, two guys, one perturbation is backscattering in the first and second channel, one perturbation is in second and third, and so on. It turns out that this you can solve immediately accurately. You need, so you say 3 relevant perturbations, so 4 channels, so 1 remaining free field, and it needs to be orthogonal to all of them. It's a trivial geometric sequence. This is, I didn't even write it down. So this is the answer for these guys. It's a different answer. You see that still you have just 2 numbers, but you can play with it. And this is, for example, small numbers, rather small numbers, very close to 1/2. Rather close to 2/5, rather close to 1/6. Reasonable perturbation, less reasonable, even less reasonable, because you understand that the scaling dimension goes up, which means that you need very small latitude parameter. What does it mean, very small latitude parameter? Extreme interaction strengths. So maybe you have some small point on your phase space. So this is reasonable deviations if the experiment. If you believe to the experimentalists, they say only 2 channels, this is the only one result which exists. So let us try to see. So obviously I don't have here 1/2, but how close can I come? Exact 6%. This is much larger than the error which they report in their result. This is huge. You cannot get it. You say, okay, maybe you are not exactly as Sergey asked me at the first minute, what will be other numbers? So how many numbers we have? 2 times infinity, yes, so we can substitute. So please, have you exactly 1/2, exactly 1/6, but I cannot even imagine what will be the scaling dimension and in which universe it will happen, and it takes. So reasonable deviations, but impossible to have perturbations. Okay. This is the comparison which I was talking about. And just to conclude, but I actually already concluded in some sense. So this is the most important part. We have now 2 approaches, but first of all, we have S matrix, in my opinion, perfect, proven that you have frozen fields, you know your answer. And it depends only on the frozen fields which you were provided by the experimentals. Kubo formalism still, I believe, very important, and I think this is the first approach proves the second one. As I said, we need relevance and coexistence of these channels, and as I said, if I have exact even denominators, then I need to have at least n equal to 6, 3 full spin channels. Thank you very much. Now I am done, and I invite my.
Thank you, Vita and Igor, for a nice presentation. Lots of questions, but maybe we can still allow for more if. If not, then we always. Okay, yes, please.
Just one question. Maybe if you make this channel more wide, probably you can have situation with 4 full spin channels, and probably can you do some prediction for some other numbers for experimentalists? Or this is
no. There is this. The formula was produced already by Oregon Shavit. This is the formula which I have shown you. N capital minus in the numerator, you have sum of n's in each channel. In the denominator, you have sum of their squares. So you can play, and obviously the moment you over 5 channels, you can produce all, you can produce even denominators and what you wish. But obviously, it's much more interesting what would happen if you have combination of few perturbations. In my opinion, you need to stay at rather small number of particles, because imagine, if you are talking about one particle being backscattered, it's normal, it's reasonable. 2 particles being backscattered simultaneously in different channels, it's already probability squared, yes? So this is the point. The second point, you need momentum conservation. The third point, you need the perturbation to become relevant. So it's really, in some sense, limits you, but you have infinite number of answers. So we can write any answer solution.
Quick
Yeah, please.
addition. Absolutely right. I agree. Just you kind of anticipated what they claim is the main result, why they see what nobody have seen before, because they claim that they still have 1, 2, 3 channels, not many, but they make it shallow. They make it shallow by weakening confinement, right? So the confinement becomes more and more shallow on the top, but they are, and definitely you are making distances shorter and shorter between levels of transverse quantization. If you want to keep the experiment in 2 or 3 levels channels case, you also play with top gates. So they do all this stuff, and the difference is that what you get few channels, but very shallow, very low density, and in one dimension, the lower density, the higher role of the interaction. If you just compare kinetic and potential energy, when you decrease the density, you go into strong interaction link.
Any more questions?
So
Maybe, yeah, you have a question?
2 questions. So one is as in experiment, do you know how it makes the plateau become like more pronounced? When plateau become like in quantum world, we know the plateau appear because of disorder. How about in this case?
That's a good question. They appear because they do not depend on the asymmetry of the potential. So these are not plateaus of quantum Hall when you just change Fermi energy or you change magnetic field or you stay close. This is, let's say, it's in some sense, it's additional parameter. But lucky for them, they were able to observe these special numbers. Igor.
Yeah, so if you look at, forget about interaction, that's a separate shit, even if it's non-interactive. The particles are coming from several points, right? Potential is parabolic in this direction along. That's the confinement. Current goes this way, but you also have inverse parabolic potential in direction parallel to the current. That's kind of saddle-point barrier through which electrons are coming in this 2-dimensional space. So you have 2 parameters. One is the how steep in the potential in the direction of the current. It tells you in a sense how long your 1-dimensional line. In transverse direction, you are talking about how well separated levels of transverse quantization. So one parameter tells you how much change you can make without changing number of channels, and that's how wide the platter. And the other parameter, which controls length, tells you what the width of transition between 2 platters will be. So they play with all these parameters.
So basically, if you make the longer, then you can have like
Yes, yeah. But they cannot make them too long because first of all they have this measure of of migrant, and second, you should not go over the length of equilibration, right? If relaxation length becomes shorter, then you lose everything.
You have a Boring effect. You have a Boring effect. I scatter on the boundary of these double numbers and spokes.
Scattering from what?
So scattering on the event is a very long channel, physical channel. You can have scattering on the boundary of the channel.
That's a separate issue. They claim that they have all dopants so far that all effects of dopants, which they always have in oxides, are fused, right? And adiabatic limit, no really setting.
I have another question regarding the temperature dependent. You have the temperature.
Yes, you mean the one of the first ones, yeah.
Yeah. You understand why at very low temperature go to
Kind of, yeah. So first you start high temperature where you can forget about any interaction. It's weak perturbation. Then you lower temperature, and if it happens that the perturbation is relevant, it means that it will blow up this lowering temperature, it blocks everything. Then you get in the limit where you effectively cut your wire into its. Then you are in if you want still to take into account weak current, you are talking now not about backscattering by barriers, but rather about tunneling through the contact. So like in Lagrangian, you switch language from barrier to a tunneling, and you have to calculate now scaling dimension of the tunneling operator. It turns out that it becomes relevant, and you
Go back.
go back to where you started from. But
And
it's-
has this been observed experimentally?
No,
No.
And what is the predicted temperature for the, let's say for the setups of the experiments where you have some guesses about the numbers of channels and other things, what would be the estimate for this temperature at which this is?
okay, I know the estimate. I mean, I know how it looks like. I don't know figures. Definitely, it should be extremely low temperature.
Number. What is the, first of all, the temperature of the experiment?
It's 10 millikelvin.
And 10
10
millikelvin.
millikelvin,
And what is your extreme low temperature?
100 times smaller.
100 times, which is doable in principle.
No.
Oh.
I know about. I have no idea about any experiment below 5 millikelvin.
Okay,
Or 2 maybe, but that's best. Yeah, so no, they didn't see. But again, estimate is very rough. This estimate is based also on the amplitude of the perturbation. Right?
but like this super low temperature, do you expect like the thing before you apply get can be like in super thin phase, super low temperature,
It's super much.
and then like the thing that before you apply get it can be supernovated. Does it
No,
like the-
sorry. The lowest, maybe I misunderstood. The lowest temperature that they have 5 millikelvin.
what controls this super low temperature? Can you, in other words, could you tell how to increase it so that you can finally see it? You could make it 100 times big, still maybe keeping other effects or getting it closer to the millikelvin.
Honestly, I have no idea. I have seen in Arce, half of this room, the device, which does something, and they claim that 5 millikelvin, that's the best.
No, what I'm asking is you have.
How to change the
You
sample.
have an estimate and you say that this super low temperature is 100 times smaller. I don't know where this comes from, but my question is, can you therefore tell what the experimentalists have to do in order to increase this number?
So why is the temperature is small? Because it's proportional to exponential of minus, and then just for you, mass of solid. If you treat the problem classically, if you think about wave propagation, sine-Gordon problem, you have this cosine, potential cosine. If you think that it's like sine-Gordon problem, you can find mass of the potential, mass of the solid, which is, I understand, proportional to either square root or amplitude of the cosine itself. Right? Estimate is based on assumption that the amplitude of the cosine, like typical Coulomb energy in this system. Don't know whether it can be controlled, and if you lower, you will probably lose all effects of interaction.
Okay, thank you.
That issue.
More questions? There's still two Zoomers hanging around in Zoom. Any Zoomer questions? That's not the case. Then let's thank both speakers again. Thank you very much. I have no idea whether we have food outside.
Yes, announcement. There should be food, maybe not right now, but in 17:30 probably.
Okay, very good. So
At
there
least
will be food outside.
There is a letter from Galen, at least with this. Куда мне положить?
Тут написано, this is